Okay, so the big news of the day is that Wednesday is exam one. Um, and the topics are everything up through um, strain and constitutive relationship. So the stuff we're doing right now, principal stresses, is not going to be on the test. Anybody have any questions about the test? Okay. So I have a couple of questions people have asked about principal stresses. Before I do those, does anyone have any homework questions you'd like me to go over that will be on the test? So these would be a little bit old, a week old or whatever. Okay. So the first one was number 2 in principal stresses. Yeah. Okay.
Compared to like last semester for the test, like how much time do we get on the test? Will it be longer?
Yes.
Do you have more class period or?
It'll be, well, yes. On an 80-minute test, I'm trying to write something that'll take about the average person in the class 60 minutes.
Okay.
So I'm telling myself, like, I want about half the class to have already turned the test in an hour into the test. That's what I'm kind of shooting for. But you have 80 minutes to work on it, probably 90 really, depending on my mood. So yeah, any other questions about it? But definitely, it will feel longer if you don't have these matrices at your fingertips in your calculator. That is for sure. So if you don't have that set up, you should try to get that set up before Wednesday and get a little practice doing it with your calculator. Okay. So the question, the first question was on number 2 from principal stresses, and number 2 depends on number 1. So I'll just go through it. It's good review stuff for the test. So okay, first we have to calculate the compliance matrix. And this thing has an undeformed height of 0.25 meters, a width into the page of 0.1 meters, and a thickness of 0.005. And it's put into 8,000 newtons of tension along its vertical axis. I'm going to use a coordinate system like, so here's my x. And I'm going to call y going this way, and z going straight across. I'm just doing that because the numbers that it gave me for deformations and stuff are in this y direction. So to calculate the Young's modulus, the stress is going to be 8,000 divided by 0.1 times 0.005. And so that is 1.6 times 10 to the 7 pascals. And then the XX normal strain is the deformed height of 25, 0.25, 022 minus 0.25 divided by 0.25. So that is 1, 2, 3, 3 zeros, and then so that is 8.8 times 10 to the minus 4 unitless. And then EYY is 0.09998 minus 0.1 divided by 0.1. And that is negative point. Okay, something here. What is going on? 0.9099998. Oh, because I did it twice. So this is negative 2.0 times 10 to the minus fourth. Okay, so now we can calculate the Young's modulus. Is 1.6 times 10 to the 7 divided by 8.8 times 10 to the minus 4. And that is 1.82 times 10 to the 10th pascals. And then Poisson's ratio is negative of negative 2 times 10 to the minus 4 divided by 8.8 times 10 to the minus 4. The 10 to the minus 4's cancel. So you just have 2 divided by 8.8, which is 0.227. And that's unitless. And so now we can go on to number 2. Okay, and now, so the material is, we know what the material behaves like now. We have E and nu, and we can calculate the compliance matrix, which means we can calculate the stiffness matrix. So we have if we know the full stress at a point, we can calculate the full strain. If we know the full strain, we can calculate the full stress. And now we're saying that material that we've defined has this state of stress. And we want to calculate a few things. The strain at this point, the principal stresses. Well, I just went through that whole thing about you guys should have this all programmed. I don't have this programmed in my calculator currently. I think, let me just, so now we're going to go, I'm going to just sort of write what you would do, but to find the strain, your C matrix is going to be like your compliance program for a Young's modulus of 1.82 times 10 to the 10th and a Poisson's ratio of 0.227. And then with that compliance matrix, you'll go the Voigt strain is equal to the compliance matrix times the Voigt stress. And the Voigt stress would be, this is in megapascals. This is a really important thing with using the compliance matrix. We're almost always using a compliance matrix that has units of pascals. Really, 1 over pascals is the units of the elements. And so in order to have your units match, your stresses need to also be in pascals. We're often talking about stresses in megapascals, so you have to make that conversion. So our Voigt stress would be negative 20 times 10 to the 6, 0.4523 times 10 to the 6, negative 14.5477 times 10 to the 6, and then 2.5652 times 10 to the 6, 0, 0. And that'll give you the Voigt strain. Any questions about the first part? And now, what are the principal stresses and the corresponding principal axes? So this matrix is negative 20, 0, 0, 0.4523, 2.5652, and then 0, 2.5652, and then negative 14.5477. And these are in megapascals. And what I got out was negative 14.9743, 0.8789, negative 20. And now I'm going to come up with the corresponding axes. Those are the eigenvectors. So do eigenvectors of that same starting matrix.
What happens if our eigenvalues are in order, like with Wolfram? I think my first eigenvalue was negative 20 or...
Yeah. Okay, yeah, let me talk about that. So yeah, these can come up in any order. And not only that, the corresponding eigenvectors can come up in either direction parallel to what it gives you. Okay, so here's what it gives me. So any eigenvalue, eigenvector calculator you use is going to give them, whatever order it gives them, it's going to give the matching vector to the value. So I got 0, 0.164, negative 0.986. And that corresponds to...
Wait, is that in the calculator?
Yeah, that's just coming out of my calculator right now. And then the second one, corresponding to 0.8789, is 0, negative 0.986, negative 0.164. And then the third one is 100. Well, there's six different permutations of these three eigenvalues. Yes.
I got something different on Wolfram Alpha.
What did you get?
They're me. They're just probably different order.
Well, I got for first one 1 0 0, and then the second 0 negative 0.166
Mhm.
1, and then the third 0 6.01.
Yeah. Okay. Okay. So these are Wolfram Alpha is doing something. I don't know why it does it this way, but these are way more useful if they're unit vectors because we're going to end up using them as coordinate system axes. Wolfram alphas are not unit vectors. So you would have to calculate the unit vector in that same direction, and then you would get the same thing. Okay, I think they're doing it with just one of their magnitudes being 1. Okay, so then you have to divide by the length to make it a unit vector. So let's do a couple of possibilities. So there are 6 permutations of these 3 eigenvalues. So you could have the first one in the x, second one in the y, third one in the z. You could have the first one in the y, second one in the x, third one in the z. You could have blah, blah, blah. There's 6 of those separate orders. Okay. So probably the most obvious way to go would just be whatever order it's in, I'm going to call that my x, y, and z. So my principal stress tensor is going to be negative 14.9743, 0.8789, negative, 0, and then 0, 0, negative 20. Okay. And then if you wanted the coordinate system that corresponded to that, you could make this your x, this your y. So let's say it is the x-axis would be 0, 0, 0.164, negative 0.986. The y-axis would be 0, negative 0.986, negative 0.164. And the z-axis, how do we know what the z-axis is? It's either going to be 1, 0, 0 or negative 1, 0, 0. You could get that by taking the cross product of these two and seeing which one it is. This is basically in the negative x direction. This is basically in the negative y direction. Negative z. So in, down. So this would be negative 1, 0, 0. Just based on the right-hand rule.
Could we also make it in the positive direction too?
What?
The z-axis?
Well, okay, so these eigenvectors they give you can be in either direction. But the thing is, if you're going to use them then to define a coordinate system, you have to make it a right-handed coordinate system. So that's what I'm doing here. I'm just saying x can be either direction, so I'll take what they said. Y can be either direction, but then x cross y has to be z.
Because it has to be a cross product of the two other axes.
Yeah, exactly. Just because of the right-handed coordinate system rules. Another way you could do this is
when you do the eigenvalues, it gives you the principal stresses and also the vectors, like those values from the equation, they give you both.
Yeah, they give you both. Yep.
Oh.
And you have to remember that each axis, so you can change the order of this stuff, but you always have to keep the same axis corresponding to the same value. Okay, so here's another way you could do it. Make it as similar as possible to the original. This first way is, so one way is just use their order, the order that you're given. Another way to do it would be look at these axes. This one is the x-axis, so the axis it's most similar to is the original x-axis. So I'm going to say my coordinate system axes are 1, 0, 0. The one that's closest to my y-axis is the opposite of this one. So 0.986, 0.164. The one closest to my original z-axis is the opposite of this one. So that's 0, negative 0.164, 0.986. And these have to, the value and the vector have to stick together. So the 1, 0, 0 has the value of negative 20. This one has the value of 0.8789. And this one has the value of negative 14.9743. And so using this approach, my principal stress tensor would be negative 20, 0.08, nope, yeah, 0.8789, 0, negative 14.9743. Those are 2 of the 6 possible permutations. One thing to notice is you can multiply the vectors by negative 1 to make a right-handed coordinate system. But the values stay the same. Okay, so you're not multiplying those eigenvalues by negative 1, only the eigenvectors.
So yeah, there are 3 different ways we could set it up, and we can also double that by multiplying them by -1, but keeping the principal stresses the same.
That's true. Yep, that's true. So basically, I guess I would say there are 6 different stress cubes that this can show. Okay, well, what if we wanted to know? So notice that the x-axis stayed the same, right? Why is this doing that? Hold on a second. Oh my God, is this about to crash? That doesn't happen to me in a long time. Let's see what happens. Okay. All right. So what we have here is, since that x value stayed the same as our original value, we have a principal stress tensor that's rotated about the x-axis from our original one. So what's the angle that it's rotated? We've done one example of this before. Let's take a second. This isn't asked in the problem, but will everyone just take a second and see if you can think through the geometry to figure out? So what we have is a principal stress tensor, a principal coordinate system that's just rotated somewhat, a little bit, from the original coordinate system. See if you can think through how much it's rotated. And feel free. Yeah, let me help you visualize it. So here's our starting coordinate system. It's rotating about the x-axis. So I'm going to draw it a little funny with the x-axis coming out, the y-axis going that way, and the z-axis this way. And that satisfies the right-hand rule stuff if you check. So, and then our new coordinate system, these are the axes. So the new x-axis is the same as the old axis. The new y-axis is mostly in the same direction as the old one, but points up a little bit. So this is like our y principal. Our x principal is the same as, and then our z is just a little bit in the negative y direction, mostly in the positive z direction. So it's like this. Okay. So that's the difference between our original coordinate system and our principal coordinate system. So now, okay, so the inverse cosine of 0.986 is, what did you say, 9.4 degrees?
9.4, yeah.
I got 9.6.
Exactly?
Oh, no, not exactly. It's not
5.1?
986.
5.9?
I guess maybe my values were different. I used 0.164.
Oh, okay. Yeah, there's some round off here, but whatever, it's something like this, you know. So that's how you can tell how much the principal coordinate system is rotated from the original coordinate system. It's really it's not useful in any circumstances. It's especially not useful if you don't have one axis that stays the same. But if you have one axis that stays the same, it's just one simple rotation about that axis, and you can calculate that angle.
So that would be essentially the same as tilting my phone up a little bit if this was a cube, right?
Right, exactly. Yep. Okay, what else? What else are we talking about here? So we got the principal stresses. We did the thing with the coordinate system. What's the strain in the new principal coordinate system? So now you would go.
It's now run the D already.
Yeah, the new.
Draw the new stress element in the principal coordinate system. Well, yeah. So I don't try to draw these elements rotated. Just draw it the way you're used to it. But this would be like, so you have -20, 0.8789, and then -14.9743. So principal stresses, draw this. So this is the principal stresses. That would be part B. This is part C. What's the strain? So you don't have to do anything to the compliance matrix. The compliance matrix is just a thing that represents the material. So the Voigt strain in the principal coordinate system is just the compliance matrix times the Voigt stress in the principal coordinate system, which is negative 20, positive 0.8789, negative 14.9743, and then 0, 0, 0. Any principal stress has zeros for those last three elements in the Voigt representation. And then last, rotate 45 degrees about the axis corresponding to the middle eigenvalue. What's the stress tensor? This stress tensor contains the maximum absolute value of shear stress. Okay, so what we're going to do is...
Be the Q matrix or something?
Yeah, so that's what, so we're going to do the Q, multiply the Q matrix, but the first thing we have to do is figure out what axis we're rotating about. So what's the middle of these? The minimum is negative 20. The maximum is 0.8789. So this is the middle. Okay. And so I'm going to rotate 45 degrees about the Z axis because this is in the Z position. So my Q matrix is cosine of 45, sine of 45, 0, negative sine of 45, cosine of 45, 0, 0, 0, 1. And then the matrix with the max absolute value of shear stress is just Q times our principal stress times Q transpose. And it will have one value at least. Well, the shear's stress has to be symmetric, so I guess it'll have two shear values that are so it'll have two shear values of plus or minus tau max, which is the maximum minus the minimum divided by 2 so that is plus or minus 10.4395. And these are all still megapascals. So if you calculate that matrix, you'll have two values, either positive or negative, that. Any questions about that?
And if we do orient them differently, choose axes that aren't set like switch around Z, Y, or any other stuff like that, our answer will probably like be oriented differently and have different positive.
Different values, right? It has to be 45 degrees about the middle axis. Right.
But it feels if it's different from like other examples or so solution, it will still be correct. We just took a different approach, right?
Well, I mean, like if you started with this coordinate system, this principal stress tensor.
If we chose like a different coordinate system.
Oh, like before this step. Yep. So whichever one, so that negative 14.93 is the middle value. And depending on your coordinate system, it could be an X, Y, or Z, but, and you have to rotate about whichever one you have, and then you'll get the same maximum shear stress value. The other stuff could be different, but you'll still get a plus or minus 10.44, whatever. Okay. And then I was asked about number 4 also. So we have a stress tensor. First, draw the stress element. We have nothing going on in X. For Y, we have 1.33975 and 5. And then for Z, we have 18.6603. And then what are the principal stresses and corresponding principal coordinate system? All right, so I'm going to calculate these values and eigenvectors, and then we're going to take a minute for you to come up with coordinate systems and stuff like that in a couple different ways. So for the eigenvalues, I got 20, 0, 0. And for the corresponding,
One of them, I got like a really small number.
Yeah.
You just rounded to 0?
Yeah, I just rounded it to 0. That's what I got too. I got a 0.000007. Remember, these stresses have to be big to matter at all in engineering.
Yeah, and this one was like 6 times 10 to the negative 6, so very small.
Right. And then I'll do the same thing for the eigenvectors. And this one corresponds to 0.2588.9659. This one corresponds to 0.9659, negative 0.2588. And this one corresponds to 100. Okay, so first, so we're going to do this 2 different ways. And the first way is, let's say that our principal stress tensor is 20, and then 0 in the second diagonal, and then 0 in the third diagonal. What's the corresponding coordinate system? Okay, so take a second and see if you can figure out what those coordinate axes would be. All right, well, the x-axis, we can just use what it gave for our x value. So that's 0.2588, 0.9659. The y-axis, we can just use what it gave. So 0.9659, negative 0.2588. And then now for the z-axis, you have to think a little bit. In order for this to be an acceptable coordinate system, x cross y has to give us z. So one way you could do it is plug the cross product of those two into your calculator and see whether you get 100 or negative 100. Or you could think physically like this is basically the z-axis, this is basically the positive y-axis. So this has to be negative 100.
Can you say one more time how you did it?
Physically, yeah, I just said this is basically in the direction of the positive z. This is basically in the direction of positive y. And so if you think of those, so we have positive z. Well, let's just think of our coordinate system. There's z, there's y. Okay. So if you have z crossed with y, do the right-hand rule. Your thumb is in the negative x direction. So that's how I do.
Could you change it so z-axis is 1 and then just invert that for the y-axis? So it's a negative value?
Yes. Yeah, you can multiply any of those vectors by negative 1. Okay, so let's do it the other way now. So the other way is look at this thing, and it's pretty clear that if we're looking for the closest coordinate system to the original, then we're going to call our x-axis 100, clearly. The y-axis we're going to call 0.9659, negative 0.2588. The z-axis we're going to call 0.2588, 0.9659. And so now we just have to match up the values. So we're going to have, so corresponding to our x-axis is a 0. Corresponding to our y-axis is a 0. Yeah. And corresponding to our z-axis is a 20. This is just rotated about the x-axis.
Is it possible to have shear with only like one principal stress?
Yeah. That's
It seems like it's really
yeah, just think about it in terms of the stress cube. Like what this means is you have a material and all that's going on is 20 megapascals this way and 20 back into the page on the opposite side. So that's just like, that's what happens in a tensile test, for example. All you have is tension along one axis and nothing else going on.
okay. Is that-
Okay, and what angle? So this is just a rotation about the x-axis. What angle is it rotated? We can do that. As the inverse cosine of 0.9659 about the x-axis from the original. And so this is oops, 15 degrees.
Why did we use the point?
Why did we use the point? Because what I did was I'm just trying to figure out how far these our new axes are from our original axis. So if you set that up to just do the right triangle trigonometry, you can just use SOHCAHTOA to figure that out. Think of it like, let's think of the z-axis. So we have one going this way. That's the original. Then we have this one where this is 0.9659. This is 0.2588. We're trying to figure out this angle. And so, yeah, it's just trigonometry. Can anyone think of, so it would be a pretty weird coincidence. So I made up this starting stress tensor. It would be a pretty weird coincidence if I just made up a random stress tensor that ended up being 15 degrees about one axis from the principal stress. You know what I mean? So how would I try to think, how would I have gone about getting this original value for this stress tensor that has this simple relationship to the principal stress?
You work backwards?
I worked backwards, yep. So I started with the principal stress tensor like this.
Mm-hmm.
And then I just used a rotation matrix for 15 degrees about the x-axis, applied that rotation matrix, and it gave me this. You can think of it as kind of like a scrambled stress tensor. Okay. Stress tensor.
Do it with rotating all three directions. Like we've been knowing
Yes.
like around one
Yep.
axis.
Exactly. You can. Yeah. And you can do them right in order.
Oh, so you'd have to do it step.
Yeah.
Yeah, makes sense because of the.
Yeah. So now calculate the strains. We're just going to use the compliance matrix again. Find a stress tensor with a maximum absolute value of shear stress. Well, really what's more useful is just to know what the maximum absolute value is. So let's get that first. So tau max is equal to the maximum principal stress minus the minimum principal stress divided by 2. So that's 10 megapascals. And now let's calculate a stress tensor with a maximum absolute value of shear stress. So I'm going to start with this principal stress. What position is the middle eigenvalue in? The middle principal stress in? It's 0, so it could be x or y, right? So I could do either one. So I'm going to rotate the principal coordinate system 45 degrees about x or y. I'll do it about x. So let's say q is equal to 1, 0, 0, 0, 0.7071, 0.7071, 0, negative 0.7071, 0.7071. And so the stress tensor with the maximum shear stress is equal to Q times this principal stress tensor times Q transpose.
And if we do it with the y, it's gonna be this.
Yep. I mean, they'll be in different places and maybe you'll have negatives and stuff, but you'll still have 10s or negative 10s in the shear spots somewhere. Any other questions about that one? I think that was the end. Oh, calculate the strain now that you're in that coordinate system. So then again, you just use the compliance matrix.
So when we did D,
So D and F are both just multiplying the stress tensor that you currently have by the compliance matrix. Yeah. Any other questions about that one? Okay. Well, I don't think there's any point in going on to stuff that's not on the test for 15 minutes. So that's it. So you can go spend this 15 minutes eating ice cream at they sell ice cream bars and stuff at the bookstore, I think. So, yeah. So go there.
the bookstore, like the library.
They don't sell it at the library, I don't think. So,
There was an event.
yeah, right.
Why were we making bookmarks one day?
Okay, so test on Wednesday, and I'll put up a weekly assignment, but there'll be no daily assignment for Wednesday. Goodbye.
How put mine in? I got something different from yours. It
Okay,
was like the shears were like 5. The angle was supposed to be 15, right? Was that where I messed up? I was rotating around.
Is this for this example or the last one?
This example, yeah. But I was trying to follow along. It was supposed to be an angle of 15, right?